Good morning, Tilo Sand. Welcome back, everyone. Whoa. Good morning, Tilo Sand. One more time. Can you hear the bass from last night still? Bum, bum. Oh no, it's my heartbeat. It's fine. Still alive, still going. Good to see you all. Everybody having a good time, building up some new EIAS memories? Hope so. Hope you're having as much fun as I had anyway so far, and I'm having. So this morning we will continue with the education session, and then up until the break. So first of all, we have Arianna Astolfi, and then we have a fantastic stand-in, Rainer Machner, for Gerhard Tiesler, who cannot be with us due to family illness, and then Adrian James as well. So first of all, if I can introduce Arianna Astolfi, assistant professor with Politecno in Torino. And Arianna has been heavily involved with the Italian standard. You've worked tirelessly for, is it almost decades, a number of years to bring through an Italian standard. And now you're going to tell us about optimal reverberation time in Italian classrooms.
Thank you.
Over to you. Thank you.
Thank you.
Thank you.
I have to wait for the time.
Yes, I'm able.
No problem.
Oh, yes. I am 1 minute early. So another show of hands of if everybody's having some fun. Yeah, I'm
No, it's
ahead of myself. 1 minute, so we'll just hold on. Just noticeable difference. 1 minute. Yeah. Can you feel it? I can feel it's palpable. You can sense. Yeah, you can sense it. Please enjoy the vista. It's lovely.
Anyway, I can start.
We are good now. Good to go. Thank you. Thank you.
Thank you very much for being here. Thank you for inviting me to have a talk on my research topic. I've been working on classroom acoustics since 2000. So this is an interesting talk for me because it resumes some of my findings, and I want to share with you what is my thought. Yes, actually, I have been involved in the new standard on classroom acoustics in Italy that is compulsory by law, thanks to the work of many of us, Dario Dorazio, for example, Italian guys that do research in this field. We, in the end, did our best to have this standard approved. This is a revolution in Italy for us and for the new schools and the learning of children. So we are very proud of that. But my talk is not on the standard on classroom acoustics. In fact, the standards has been presented many times in talks and journal and so on. But I want to do a focus on one aspect of the standard that is anyway that can be improved in the future if it will be good to do. And particularly is the optimal reverberation time in classrooms. But what about the standards? The standards UNI 11532 and DIN 18041 say that, for a small sized classrooms of 200 cubic meters, more or less, the optimal reverberation time in occupied conditions should be around 0.36 seconds. Do you agree? Okay. As far as the frequency content, it should more or less flat, but we can tolerate, we can tolerate to have plus 20% and minus 20%. So that we can go up to 0.7 and we also can have 0.5. Well, I'm telling you about 0.7. That for me is the best, but I have some background for saying this. Okay, for example, we can go back into 2009, Young and Bradley. Bradley, one of the most famous researchers in the field of acoustics. What did he say? What did they wrote in JASA? That when the source of noise are nearby children, so babble from children themselves, is the most occurrent noise source in classrooms. That is, the noise is very close to the listener. So only and mostly the direct energy affect her speech signal to noise ratio because it is very close. Do you agree? And this is the reason why they found that in this condition, the optimal reverberation time should be between 0.3 and 0.9 with an optimal value of 0.7. But why? Because in order to have a very good speech signal to noise ratio, we should have more reverberation because the noise is almost constant because it is direct sound and it is very close. So that we should have to improve the signal with the reverberation time. But reverberation does not affect noise because it is very close, so does not affect so much. And this is the graph by Bradley and Young, where you can see that for primary school children and adults, we have a maximum around 0.7 in speech intelligibility. Yes, speech intelligibility. But another study by me and my group, dated back 2012, we soundproofed classrooms and moved the reverberation time from 1.6 to 0.4. But when we tested children in field with speech intelligibility test, we found that with bubble noise, we did not have any improvement in speech intelligibility after soundproofing. And instead, with traffic noise, we did have 10-12% of improvement after soundproofing in speech intelligibility. But the traffic noise source that we used to simulate traffic was outside the room, on the balcony. And instead, the noise of bubble was exactly in the middle of the room, close to the children. Curious thing. But another thing is that optimal reverberation time of 0.75 minimizes the speech level of the teacher, so the vocal effort. Yes, across 4 different studies, we found that, look at this, the vocal effort has a minimum in reverberation time of 0.7. But why? Because with reverberation time lower than, the speaker lacks of support from the room. And when reverberation time is higher than, there is too much noise due to amplification, and it starts the Lombard effect. This is another study with different teachers. We monitored the teacher's voice. And this is the third one, and the fourth one. This was a longitudinal study with secondary school teachers along the beginning and the end of the school year. But another study, again, to prove that 0.7 seconds could be good. We tested 13 primary schools and 29 first grade occupied classrooms with different acoustic conditions and different shapes, but a volume around 200 cubic meters. Yes, we put the tall box. At the height of the teacher, we put microphones along the main axis of the room and in other position. But we wanted to investigate what happened along the main axis, the slope of the speech level. We wanted to investigate the slope. Yes, and this is the central position, of course. And oh yes, we put another microphone position exactly at 1 meter from the source, at the same height, the reference. Okay, we measure T20, C50. Speech level, thanks to the steeper male signal, of course, at normal vocal effort. And the slope of it, MLS. Noise level in silence and during group activities, averaged across many positions in the classroom. And U50 obtained, that is very similar to STI, that is obtained from C50, noise level and speech level. Always along the main line and in the central position. So this slide is only to show you that we covered quite a big range of reverberation time, okay? Not solely only a small range, from 0.5 to 1.4 occupied. These are graphs of C50 and U50, and again, we covered quite a good range. After we decided to choose an arbitrary threshold of reverberation time occupied, arbitrary, 0.8 seconds, we divided classrooms in two groups, compliant and non-compliant, with this threshold. So that compliant ones were classrooms with reverberation time lower than or equal to 0.8 seconds. Non-compliant were classrooms with reverberation time occupied higher than 0.8 seconds. But why we decided to use this threshold? Because of many reasons that are listed in this slide. According to literature, for moderate requirements, it's good. Yes, we applied statistics, of course, to investigate if the two groups were different. Human Whitney test, for example. And look, okay, differences, significant differences, were found between the two groups with respect to, of course, reverberation time, occupied and empty. This is the background noise during group activity. This is C50 as average value, mean value across the positions, central position, U50, mean value and central position. But we did not discover any differences with respect to noise level in silence. It was very low, not so low, but low. Speech level at the reference position, remember, at 1 meter from the speaker, at the same height, and we did not discover any differences with respect to the slope of the speech signal. Look at the slope of the speech signal for the two groups, compliant and non-compliant, is the same. It is minus 2 dB per double distance. Of course, we checked the signal-to-noise ratio at the back of the room. It was enough to have the signal measured, of course. And yes, it is the same, minus 2 dB per double distance. For the two groups, exactly the same. And look at this. We obtained sound strength, thanks to a procedure well explained in the paper by Bradley again. Yes, we obtained the sound strength total, and of course, we obtained exactly the same slope as the speech level, minus 2 dB per double distance, because it is a level, of course. But we further investigated the G early, and we obtained minus 3 dB per double distance as a new slope. For G early, that is the sound strength related to the first 50 milliseconds of the impulse response, direct sound plus early reflections, minus 3 dB per double distance. And G late, that is related to the strength of the late reflections. Of course, the slope changed for the two typologies of classrooms, but also the level changed. In fact, you can see for non-compliant is higher than for compliant classrooms, G late, of course. But what I want to show you is that for good speech intelligibility, look at the position at the back of the room. In the case of non-compliant classrooms, G early and G late overlapped, but it is not good for speech intelligibility. It is not good to have overlapping of G early and G late because of the masking, okay? And this is not good. So we decided to look at the back of the room. Look at the back of the room. Look at the position like 6 meters from the source. Look at the back student. We, in this slide, can see for 6 meters from the teacher, G total, G 50, and G late. But we want to have a difference between G early and G late. But how much? At least 3 dB. But, okay, we investigated for all the range of reverberation time, what is the range of reverberation time that allowed for having at least 3 dB, but even to 6 dB of difference between G early and G late for having good speech intelligibility. And what is this range? Look, this range is 0.7, 0.9 for having this difference at the back of the room that we should have for having good speech intelligibility. And we also used U50 at the back of the room and a long reverberation time. And we can see that in the same range, U50 ranges between 0 and 2 dB. So optimal U50. But if we take into consideration the middle of this range, what is the middle? 0.75 seconds. And what is the best U50? 1 dB. But the story is a circle. Look, conclusions. An optimal reverberation time range between 0.6 and 0.9 has been found for primary school classrooms, which maximizes the difference between G early and G late at the back of the room, between 3 dB and 6 dB. But the central value of this range is 0.75 seconds and corresponds to U50 of 1 dB. But U50 of 1 dB was already indicated by Bradley in 1999. And okay, this is optimal for speech intelligibility when the noise source is nearby children. Remember the first slide I showed you, 0.7 by Bradley and Young, and for the low vocal effort. But what is the main advice that I can give you? Is to look at the back and to improve early reflections at the back and to reduce late reflection at the back. This could be good, not to have optimal reverberation time of 0.5 seconds. Thank you so much for your attention. I want to invite you to Torino, Forum Acusticum 2023. I am the general chair, and you will be welcome to my town from 11 to 15 of September. Thank you so much.
Thank you, Arianna.